Dear student, today we see that the conformational analysis. Okay, the conformational analysis is actually for carbon-carbon rotation. Okay, it's a CC bond rotation. The carbon actually non-metal. Among the non-metal that is for covalent bond. So the covalent bond, there is a covalent bond for two types. One is a sigma bond, another one is a pi bond. The sigma bond for axial orbital overlapping or axial overlapping, and that the pi bond or sidewise overlapping or that lateral overlapping. So from here, the sigma bond are easily rotating, but in the case of pi bond cannot be rotate. Okay, because there is a restricted rotation. So that's why that the restricted rotation of that alkene with unsymmetrical substituent, that is shown by the geometrical isolation. Okay, then next see the CH4 molecule here, that the carbon such as sp3 hybridization. sp3 means it's a geometry as it's a tetrahedral geometry. So whenever the carbon has sp3 hybridization, that carbon or tetrahedral geometry. See CH3. From here, each carbon has sp3 hybridization. This carbon has sp3, this carbon has sp3. Anyway, this methane molecule geometry, there's a carbon, hydrogen. Anywhere a molecule possesses sp3 hybridization, here any two bond are on the plane, remaining two bond are off the plane. That means one bond is above the plane. Here this bond are above the plane, this bond are the below the plane. Okay, so similar like that, we go to the ethane molecule. This ethane molecule, here is carbon, there is a hydrogen, and here is a carbon and a hydrogen, that is a below the plane. This hydrogen is a above the plane, this for below the plane, this hydrogen for above the plane. Okay, so that is for fine wedge method molecular representation. So from here, the carbon is only a single bond are presented, such as there is a sigma bond. So we already studied the sigma bond are easily rotating. Okay, so for that reason, the saturated aliphatic hydrocarbons are can be easily rotating for every 60 degree, can be rotating every 60 degree. Every 60 degree gives, there's a new conformer, that's for new conformer are given. Okay, so this is a major important. So yeah, there is a representation as two types. One is for that Fisher projection, Sahar's projection. Another one is Newman projections. Step by step we can study that both two conformers. Okay, so now we go to that. There is a Sahar's projection, Sahar's method. Here there is a Sahar's method. The carbon, here is a hydrogen, here is one hydrogen, here is another one hydrogen, here is a carbon, here is hydrogen. So in this case, this bond and this bond are the same axis. So this hydrogen and this hydrogen, this hydrogen and this hydrogen. So from here, that is a dihedral angle that is equal to 0 degree. So if we rotate any one carbon as a fixed, another one carbon as can be rotating the 60 degree. We already studied every 60 degree, it shows in the new conformer like that. Okay, so this carbon can be fixed. It's a carbon, hydrogen. In this case, the 60 degree means this way is came the hydrogen. So now compared to this hydrogen and this hydrogen, there is exactly 180 degrees there. So these two hydrogen, and compared to these two hydrogen, that is for 60 degree. Okay, so anyway, whatever that is for the anti-conformer, or this came to the this is a eclipsed conformer. This is a staggered conformer. Okay, so from here, the staggered conformer are more stable compared to the eclipsed conformer. There is a staggered, so more stable compared to there is a eclipsed conformer, because the eclipsed has 0 degree. So that's why there is a dihedral angle or the bonded electron repulsion as a much more higher compared to that the staggered conformer. So whenever the molecules are the most strained, that is a less stable. Okay, so now we move to that the Newman projection. In this case of Sahar's projection from here, this Sahar's projection of eclipsed hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, hydrogen. So we see the molecule from here. Okay. So now this carbon is hindered by this carbon. So this carbon is shielded into this carbon, and this hydrogen is whatever that. Okay, so we can get the front carbon. This for front carbon. Here is a hydrogen, hydrogen, hydrogen. So there's a backside carbon. So this carbon, this representing, or this front carbon is hindered by the backside carbon. Okay, so similarly this hydrogen and this hydrogen, this hydrogen. Actually, the exactly backside of this hydrogen is appeared, but in our convenient, we have to written at the smaller size. Okay, so here this hydrogen bond angle, that's theta is equal to 0 degree. So this is a eclipsed conformer. Okay, so from this eclipsed conformer we can rotate the 60 degree at the backside carbon. Okay, so what we can get, this is a hydrogen doesn't change, but that backside hydrogen it can be changed. Here see the hydrogen angle, this for 60 degree, but this for that 180 degree. Okay, so anyway, so this is a staggered conformer. Okay, so comparatively this staggered conformer are more free in that bond, but in the case of eclipsed conformer, that exact bond backside another one bond is all presented. Okay, every chemical bonding it is a electron cloud density. If you assume there is a substituted ethane, there is a CH2A and CH2B in this molecule. Here this carbon and this carbon, there is a representing, here is a carbon, hydrogen and hydrogen. Here is a representing as a A. This is a carbon, B as a hydrogen. Here anyway, this A and B at the angle of here there is a 0 degree. That is for fully eclipsed conformer. Okay, so because there is a diagonal angle as a 0 degree. Okay, then next, if you rotate this molecule as a 60 degree at any one carbon, this carbon is rotating the 60 degree. So what did happen? That's a carbon A, here is a hydrogen, and here is a carbon B, here is a hydrogen, here is a hydrogen. So now this A and B, actually this bond angle as a 60 degree. Okay, this A and B as a 60 degree. So this 60 degree, that's for there is a Gauge conformer. Okay, so this Gauge conformer is a little bit is a more stable because of this the bond strain is a little bit is a relief. Okay, so this is a Gauge conformer. Okay, so the next next category, if we see this molecule is again rotated at 60 degree. The conformational analysis means, let's say every 60 degree we can get the new conformer. So here is a as fixed, it's a carbon, hydrogen. This carbon can be rotated. Here is a B, here is hydrogen, here is a hydrogen. So now this A and B can be theta is a 120 degree. So this 120 degree is nothing but for there is a partial eclipse. Okay, partial eclipse conformer. Okay, so the next case, this molecule can be rotated again, there is a 60 degree. Okay, this molecule can be rotated again the 60 degree. So we can get that A and there is a carbon, hydrogen. Here is a, that is for this hydrogen. Okay, so again this B is come to here, and this hydrogen is there. So here is a B, here is hydrogen. So whatever that, here A and B as theta is equal to 180 degree. Okay, so this exact 180 degree for that is nothing but there is a fully or there's an anti-conformer. Okay, so this anti-conformer are that most stable. When that is a most stable, if molecule or hydrogen bond, there's a stability order. If a molecule possesses a hydrogen bond, it's a stability order. That's for Gauge conformer is a most stable, then anti-conformer, then next day that's for a partial eclipsed conformer, then next fully eclipsed conformer. Okay, this is the order. So in case of otherwise, if not presented in that hydrogen bond, if not present in the hydrogen bond, otherwise it's a stability order. For there's an anti-conformer, then next Gauge conformer, then next there's a partial eclipsed conformer, then next there's a fully eclipsed conformer. Okay, so this is a without. Okay, now see that the Newman projection model. There is a height A and carbon, hydrogen, and here is a B, hydrogen. Theta is equal to, there is a 0 degree. It's for that there is a fully eclipsed conformer. Okay, the next we can rotate, there is a 60 degree. There is a A and carbon, hydrogen. Now this B become here, there is a hydrogen. It's for that Gauge conformer. Then again there's a 60 degree rotate this Gauge conformer. We can get there is a A and carbon, hydrogen. Here is a the B and here is a hydrogen. There is a hydrogen. Is for that partial eclipsed conformer. This partial eclipsed conformer again rotated that 60 degree. There's a A and carbon, hydrogen. Now this B here, there is a hydrogen is there. Here is a hydrogen. Now see this. A and B, all there is an anti-position. So it's nothing but there is a anti-conformer. Okay, so this anti-conformer are that more free. In generally, there is a, if hydrogen bond are presented between the A and B, that is the Gauss conformer more stable than anti-conformer, then partial eclipse very lesser. That's for that the fully eclipsed conformer. Okay, I more satisfied this video. You are very familiar. Amazing. This is okay. Thank you to all. Just you can subscribe in this video because we spending that more time and etc etc. Okay, anyway, okay, thank you to everyone.